Okay, welcome back. In this lesson, we're again going to look at particle physics in an A-level perspective. But this is our lesson 2, which is looking at the particle zoo, let me call it. Good. If you haven't seen the first video, I recommend that you go and watch it. But what we're going to do here is we're going to look at the developments that took place that extended our knowledge beyond what you learned in your GCSE. So let me take our model of the atom. Let me just move our Rutherford model of the atom back a little bit and describe to you again the structure of it. We have a nucleus with electrons floating around the outside. Rutherford model of the atom. Not a perfect model, but a good model for the time being. Now, if we were to zoom up the nucleus, we need to remember here, of course, of the respective sizes of each of these things. Let me just jot that in. We have 10 to the minus 10. You might be called upon to use that knowledge. And then we have the width of the nucleus as 10 to the minus 15 meters. The electron we believe is point-like and is 10 to the minus 18 meters. And inside the nucleus, let's just do this in blue, we have a collection of protons. Let me do protons in red and neutrons in blue. Wonderful. This, of course, will be a helium nucleus. So therefore, what I should technically put in here is another electron floating around the outside, because 2 protons neutralise the charge, balance the charge out. This is a neutral atom, so we think there's 2 electrons there. Good. Now, that was confirmed by the Geiger-Marsden experiment, and in the Geiger-Marsden experiment, we were firing let's draw them here. We were firing alpha particles, well, against alpha. Okay, hold on a minute. Let me just take that bit out and show another setup, which is a gold nucleus, Au being gold, and alpha particles are flying in and being deviated. We know they're being deviated because gold has 79 positrons in there, positive charges, and alpha are 2 lots of positive charge, so therefore we have electrostatic repulsion which causes this movement. And if we are to have a more head-on collision, then those deviations will be greater. Excellent. And what Rutherford how he proved this was by predicting a model. Now that model you do not need to go into at the moment. It's far too elaborate for our knowledge. But let me bring in a graph of what he suggested ought to be happening. Here in effect was his theory, the dotted line. And you can see from this graph that there is a deviation that takes place around about here. Now, I don't know whether you can remember the previous video in which I described everything that takes place in the Rutherford experiment as elastic scattering. And when I mean elastic, I mean that the kinetic energy and momentum are both conserved in this instance. But you can assume that, in effect, what that means is there is no collision, in the sense of at nuclei impacting with nuclei. There's no actual collision between these two. There is a distance of closest approach, but no collision. However, when we do have these energies, collisions take place. Elastic. And in this area here, oops, sorry, move that again. And in this area here, where the collisions take place, is called inelastic scattering. It's where the particles came together and collide. The nuclei, sorry, come together and collide. Now, in order for that to happen, you need high energies. And those come from particle accelerators. And in the 60s, those energies were being achieved. These energies, 27.5 plus MeVs, were being achieved. And what did that give rise to? Well, that gave rise to approximately 200 new particles. Or, as I've described it, the particle zoo. Now, each week they were getting more and more particles, but they couldn't understand how and why there were so many of them. Now, the way that we work out how and why is because there is a substructure to each one of these nucleons, which builds a model which can be defined by the standard model, and the standard model brings together many combinations which each gives rise to a different particle. So let's take a look a little bit more at the substructure of, let's say, a neutron. Now, inside our neutron, we have 3 possible subparticles, and these are all called quarks. We have an up quark and a down quark, and they all have individual properties themselves. And we're going to talk about what those properties are. Now, let me show you the properties first, and then I'll define all these new terms that we're coming up with. First of all, let's call them quarks or quarks. I'll make the definition later, and let's build the properties. So we have this thing called an up quark, and we have one that's called the down. We give them symbols. The symbol is a U, and the symbol for the down is a D. It also has a certain charge. The up has positive 2/3 relative charge. So I'm going to write charge here, Q. I hope you're okay with charge being Q, the symbol, and the name. The down has a -1/3 charge. This is all looking a bit complicated, but bear with us. And because there's 3 of them, the associated mass is going to be relatively 1/3 of a nucleon. This is an up and a down. You will have associated antiparticles of all of these as well, but for the meantime, there is your up and there is your down. Now we have different ways in which we can combine these quarks. They exist in 3 ways. There's only 3 ways in which we can bind these together. We have a quark-quark pairing, QQQ, which could be up, down, 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 up, 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 etc. We could have all of them being anti-quarks. Are we happy that the line means an antiparticle? Or indeed, we could have it as a quark-anti-quark pairing. Now, the reason why I've written them out like this is because actually there's a lot of information under each of these which we really need to be able to deal with. Let's see if I can just move these a bit further apart from each other. what do we have? We have, just move this one a little bit further to the side. Okay, so now for each one, what do we have? The quark-quark antiquark is called a meson. And there's a whole family of mesons which we need to be aware of. I'll define this in a minute, each one in a minute. We have what's known as a quark-quark-quark as a baryon. And the anti one is obviously going to be an antibaryon. Okay. These are 3 packets. And a baryon. Now, I think it's probably worth defining each of these right now. So I'm going to write down the definition as per the textbook so we know what's going on. The baryon is, and lastly, any of these are defined as a hadron. Definition time. Hadron are high mass particles consisting of quarks and or antiquarks. Okay, baryon. Baryon are hadrons, or hadrons, whichever you like to pronounce them as, composed of 3 quarks or quarks, e.g. protons. An antibaryon is a hadron composed of, I'm sure you've guessed it, 3 antiquarks, e.g. antiproton. And a meson, finally, is a hadron composed of a quark and antiquark, e.g. a pion. Good. Whilst we're at it, let's go back to the quark definition. It says it's an elementary particle not found in isolation. Now that's important, which combines to form hadrons. And baryons. As per the textbook, I've taken those. Now, the fact that it is not in isolation, not found in isolation, is important because that is why we have combinations appearing like this. And more to the point, you'll never be able to separate one of those from the rest of the packet, so you can only infer its existence by how it combines with others. Good. So, back to the mesons, the antibaryons, and the baryons. Now you can see here you already know the first baryon because we took a neutron and I wrote it down as an up, down, and a down. Let's write that down. So a baryon. We have a neutron, which is an up, down, down. And that makes sense that it is, because if we just look at the properties here, in terms of the charge, we have 2/3 coming from the up. We have -1/3 coming from the down, and another -1/3 coming from the other down, giving us 0, which it ought to be. Whereas the mass, each of them has a third mass, which gives us a relative mass of 1 and a relative charge of 0. Neutron makes sense. We also have a proton, and I'm sure you can work out what its combination will be in order to give a charge of +1 and to give a mass of 1. It's going to be up, up, and down. Excellent. Let's do the antineutron and the antiproton. It's being up, down, down, all antis, and anti-up, anti-up, anti-down. I hope you're happy with that concept of the line, meaning that they're antiparticles, those are. Now, with the mesons are, in order to get, there's only a certain number of combinations we've got available here. We have an up and an anti-down. We have an up and an up. Sorry, one of those needs to be an anti, because remember there is a quark and an anti-quark pairing. Or indeed we could have a down and an anti-down. Or we have an anti-up and a down. So those are the three we've got available. This is going to give a charge of 2/3. And an anti-down is going to give us a charge of -1/3 minus, so that gives us a charge of 1. So these are all known as pions. This is a pi plus, this is a pi 0, and this is a pi minus. They're all known as pions. They're the lowest energy mesons. If we were to increase the energy, so we write this as, say, low energy. If I were to introduce higher energy, then you could create a high energy up, 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 or indeed an up, up, down, an up, down, down, or a down, down, down. And these would all come under the baryons, of which you think to yourself, well, hold on, some of those look very much like what we have already in the form of a proton and a neutron. Well, you could sort of say they are, but they're not actually. They're called something very different. These are called, this is called the sigma. Whoops, let me just find the pen again. This is called the sigma plus plus. You can see that because you'd have 2/3, 2/3, and 2/3, giving us 6/3, which gives us a 2 plus. We have the sigma plus, the sigma 0, and the sigma minus. And to give you a sense of why they're high energy, if we know, and you can remember that the proton was something like, let me remind myself, it's 938 MeV per c squared was the mass. Then the proton, then the sigma plus, which looks like a proton mass, is approximately 1232 MeV per c squared. So they're different. They are different particles, but higher energy. So these exist as our high energies, whereas these all exist as our low energies. Okay, now this high and low energy consideration, we are only really interested in the low energies. Those are the only ones that exist. These are the ups and the downs. However, at once upon a time, and there still exists, but only when you have high energy collisions, others which are much higher energies. And what I will do is I will start to write down what's known as the standard model. Right, the standard model. So, let me write down generation. In other words, how much energy do they have? First generation. We're going to look up the quarks first. And the first generation quarks are very much the up and the down. There is a second generation, which are referred to as the charm and the strange. And there is a third generation, known as the top and the bottom quark. Interestingly, all of these on the left-hand side have charges of plus 2/3, and the charges are minus 1/3 for each of those. There is a symmetry in this system, which is very interesting. These are the only ones that we're really going to be interested in. But just so you're aware, there are other generations as well. Now, nipping back, I should have added one more bit of detail here. We believe these quarks, 10 to the minus 18 meters, sort of are point-like, they're fundamental. A little bit like the electron. And also, as you're well aware as well, let me just do something zipping off, a neutrino. Neutrino, given the symbol. Now that is known, those are known as leptons. And I suppose you ought to give them a definition. It is a low mass elementary particle E.G, electron, neutrino. Wonderful. So in a similar way, if I write this in red here, we have electron and the neutrino. The symbol is as such. It's an electron neutrino. The electron, of course. The charge is 0, -1. The mass is 0, and the mass is 0. So there we have our leptons. But the story doesn't end there, because in the standard model, let me just write down leptons. We have our first generation, which is the electron and the neutrino electron. Our second generation is the muon and the muon neutrino. Third generation is the tau and the tauon neutrino. All of them have a charge of -1, so therefore, sorry, I should have written that. And all of them, all the neutrinos have a charge of 0. Once again, these are the only ones we'll be interested in. So there we have it. That is the standard model, and we've gone into a little bit more detail explaining how we how we've increased our knowledge from not just the nucleus, but to the sub-level of the nucleus. Quarks or quarks, leptons, so we defined what we knew already about the electrons and the neutrinos as leptons now. I've given you some of the properties and the incredible number of baryons, antibaryons, mesons, all possible combinations which could come about, which produce this particle zoo. I've already listed quite a few there. We've got 3 lots of pions, which are the low energies. We've got the neutron, the proton, we've got the antineutron, the antiproton, and if we start to go up to higher levels, we've got the sigma double plus, delta double pluses, delta plus, delta zero, delta minuses, and if we went to higher and higher energies, so we would get even more and more particles that make up the 200 odd, of which there'll still be more because they still haven't been able to access some of the very high energy quarks, because in here, the standard model, of course, we are interested in the first generation, which is the only one still in existence in our energy of our universe. But if you can increase the energy significantly, you can start accessing second generation quarks and third, which then give even more exotic particles to add to the particle zoo. Right, hope that's made sense.